They did not have a shape, they were just point masses. So first a brief overview of basic concepts, and then I'll solve a few problems. Okay, so we're looking at rotation of rigid bodies about a fixed axis. So that's a rigid body, it's rotating about a fixed axis. So we'll call this the axis of rotation. Can you fix that?
I hope so.
I restarted twice, and
Sorry?
I restarted this twice, and it would just switch.
It's very odd. I don't know why that. Maybe get a new button for it. Okay, I may just have to grab the remote real quick. Yeah, I'll be right back.
Okay, that's fine. Okay, so what we're trying to do is we're trying to keep a track of really a point on the rigid body. So let's say that this point has a position like so. We rotate the rigid body, and the point ends up here, the final position. So in the process, what happens is the rigid body has rotated by an angle theta. Okay, and we are trying to understand. Well, we're trying to do something which is very similar to linear motion, but in the world of rotations. So the same formulas which we derive for linear motion are true for rotary motion. That is, there's an angular speed, omega, like linear speed, and that is the rate of change of angle. There is an angular acceleration, and it's simply the rate of change of speed. And then there's another formula which is sometimes very useful. It is omega d theta is equal to alpha. This is very similar to v dv ds equals a. So a special case of this particular formula is if alpha is a constant. So alpha is alpha c, a constant. Then you can actually integrate these equations, and there's a formula which looks very similar to the formula in the linear world. The formula is the angular speed is equal to the initial speed plus alpha. Let me call this alpha o. Alpha o times t. Okay. Omega 0 is. Thank you. Similarly, we have theta is theta 0, which is the initial angle. In the figure I showed theta o is 0, but it doesn't have to be 0. Plus omega o t plus half alpha o t squared. So alpha o is, sorry, theta o is initial angle. And then finally, the last formula relates the angular speed as a function of displacement, or in this case angle. So 2 alpha o theta minus theta o. Okay. Again, I want to remind you these formulas are only true if alpha is a constant. If alpha is not a constant, then you basically have to plug in alpha in that equation. For example, the alpha equals d omega dt and integrate that. I've often seen people using these formulas when alpha is not a constant. If alpha is a function of time, if alpha is 3t, say, you cannot use this. You have to use integration. It's only true for a constant acceleration. The second important thing is how do you relate angular motion to linear motion? Okay. In particular, we are interested in finding the position of a point on the rigid body. So this is like a top view of the object. There's a center. This is the point whose velocity I'm interested in finding. So that's the velocity. And remember that the velocity is always, in this case, tangential to the circle. So V, by the way, this thing is spinning in the counterclockwise, the clockwise direction, but the angular speed is given by your thumb. So the speed is, so it's turning this way, which means that the angular speed, to find the angular speed, you need to curl your fingers along the direction of motion of the circle. In this case, it will be this way or this way. But the thumb will either point out of the plane, so it's in the k direction, if ij is in the plane, or minus k direction. So V is omega cross r. Okay, so this is, let's call it Vp. Omega is that, and r is the vector as shown. Okay. So that is the velocity. The final thing we want to know is acceleration. So we'll use the nt coordinates for this. So vector in the t direction, so ut direction, the vector in the un direction. So the acceleration of the point P is going to be alpha r in the ut direction plus omega square r in the un direction. Okay. Okay. This is one way to write it. So another way is to write it in terms of a vector. AP is alpha, the vector, cross with r, plus omega cross r. Okay, so sometimes you know un ut, in which case you use this formula. Sometimes you do not know un ut and you only know the vector r. The vector r points this way, and you know omega. Omega is this, alpha is here. Then you can use the vector equation. So it really depends on what you have. Now for planar motion, by planar I mean the object can only rotate in one plane. You can actually simplify the formula. We are only going to look at planar motion in this course, so you can use this formula which I'm going to write here instead of using this complicated formula, vector formula. So you can write this equation as alpha cross r minus omega square r. So this is a simplification for planar only motion. Okay, any questions so far? Okay, the last thing before we start solving problems is gears. Okay, so I have not drawn gears because it takes a while to draw gears, but when I show two circles, it means that they actually have gears on them, and these gears mesh against each other, and that's how things move. For our practical purpose, it's okay to draw circles for gears. So these are two gears, and each of those gears have a radius. Let's call this RA, RB. One of them usually is the input gear, or the gear which is connected to the motor. So in this case, I'm assuming that this gear spins clockwise. Okay, that's why this is drawn in the clockwise direction. Right, the time goes this way clockwise. The way to get the direction of the angular speed is you go to point here, curl your fingers, the right hand fingers along the direction in which this arrow is going. My thumb gives the direction of angular acceleration or angular velocity in this case. So the angular velocity is pointing inward. Okay? So if this thing spins clockwise, there's a property that this thing is going to spin exactly in the opposite direction. Right? This spins this way, this will spin that way. So this goes clockwise, that should go counterclockwise. That's typically the output gear. So omega B, alpha B. So given one of them, given RA, RB, and this, you can actually find omega B, alpha B. And that's using this property that the velocity of point P can be computed in two ways. You could compute it as omega A RA. Okay, how did I get that? Well, I use this formula here. V is omega cross R. I use that formula to find velocity of a point P. But that is the same as omega B RB. Okay, so if you know, for example, if you assume that omega A is the input gear, then omega B is the unknown. You can find that because you normally know the dimensions of the gears. Similarly, the point P has an acceleration. That acceleration is alpha A R A. That should be equal to alpha B R B. So similarly, if you know RA and RB and you know alpha A, then you can find alpha B. Any questions? Let's solve a few problems. Okay, the angular velocity of the disk is defined by omega equals 5t squared plus 2, where t is in second. Determine the magnitude of the velocity and acceleration of the point A on the disk when t is 0.5 seconds. So we're going to find the velocity of A and acceleration of A. Okay, where A is this point. We are given omega is, so we just need the magnitude. We need to move the vector. Omega is 5t squared plus 2. Okay, so in order to find the we're going to use the formula which we know. V is omega r, just the magnitude. Right? So omega is 5t squared plus 2. The radius is given as 0.8. So velocity of A at t equals 0.5 seconds is 5 times 0.5 squared plus 2 times 0.8. So that comes out to be 2.6 meters per second. Okay. Okay, for the acceleration, okay, that's a vector. It has got a at ut plus an un, where at is alpha r ut and alpha an is omega square r un. So we're going to find at and an, and then we can basically take the square root of the sum of squares, right? So at is alpha, which is d dt of omega, right? This is alpha times r. So the derivative of omega is 10t plus 5t squared plus 2, so 10t times r, which is 0.8. So at t equals 0.5 seconds is 10 times 0.5 times 0.8, which is 4 meters per second square. An is omega square r, which is 5t squared plus 2 the whole square times 0.8. So an at t equals 0.5 equals 5 times 0.5 squared plus 2 squared times 0.8, which is again 8.45. Okay, so the final step is to find the magnitude, which is simply at square plus an square. You sum them up and then you take the square root. So that comes out to be, what I get is 9.35. Okay, so this problem just illustrates to you how to use the formula for velocity and acceleration for a rigid body. If that's a rigid body, a circular disk which is spinning at a certain speed. Okay. Another question could have been, can you find the position theta as a function of time? In order to do that, what you'll have to do is you'll have to take the equation d theta dt is omega and integrate it. You cannot use the constant acceleration or constant velocity formula. Determine the angular velocity of gear B when t is 3 seconds. Okay. Well, there are two ways to do this problem. Well, one is, first we can try to find the angular velocity of A at time t equals 3 seconds. So we are given the angular speed at t equals 0 seconds. We can find the angular speed and then use the formula which relates the angular speeds between these two. I written down the formula, v equals omega r, you can use that. The other way to do it is, you know alpha for A. You can find alpha for B because we know that the relation between alpha and alpha b. Once you find alpha b, you can integrate the equation and get angular speed of b. You can use one of the two methods. They both will give you the same answer. So what I will do is, I just follow my notes, which is what I did was, I found A first and then I found angular speed of A first and then I found angular speed of B. So let me just do that so that I can put the answers down easily. So omega A at t equals 0 is 15. Alpha A equals 2t cubed, and we're given that time is 3 seconds. we want to find omega A at time equals 3 seconds, and once we do that, we will then find omega B at time equals 3 seconds. Okay, so that's the approach. As I told you, if alpha is not a constant, it's a function of time, you cannot use the formulas which have constant acceleration, so we'll have to use d omega A dt is alpha A. So integral d omega A is alpha A dt, where omega A at t equals what, 0 seconds, and omega A at t equals 3 seconds, and t goes from 0 to 3. So this is 2t cubed dt, that's 2t raised to 4 divided by 4, 30, that's 3 raised to 4, which is 81, I think, divided by 2, sorry, so that's 40.5. Okay, so omega A at t equals, so this is all equal to omega t equals 3 minus omega equals 0. So this is an unknown. We are given the initial speed. So omega A at t equals 3 is going to be 55.5 radians per second. Okay. So now we can relate angular speed of A with V, because we know that V of the point of contact is omega A RA equals omega B RB. Okay, omega A is 55.5. The radius of A is 100, so I'm going to write it in metric, 0.1 meters. Omega B is unknown, and RB is 175 mm, so it's 0.175 meters. So this gives me omega B equals 31.71 radians per second. Okay, any questions? Okay, so note that I integrated the equations. I did not use the constant acceleration formula, because acceleration is not a constant. That's a very common mistake people make. Okay, last question. Okay, determine the distance the load W is lifted in 5 seconds using the hoist. The shaft of the motor M turns with an angular speed of, so omega of M is 100 times 4 plus t. So clearly what's happening is, when the shaft turns, it spins A, that spins B, that turns C, that turns B, and that causes this W to rise up, right? But because with all this gearing, it's not a very straightforward relation. You've got to figure out the relation by using the gear ratios, or in this case the radiuses of the circle, not gear ratios. So again, what we can do is, we can actually take two routes. One is, we can try to find, and we are given the angular speed of this motor, we can go through all this gearing and find the angular speed of E, which will be a function of time, and then integrate over 5 seconds to find the distance moved. The other way we can do this is, we could first find the angle turned by this motor in 5 seconds, and then use the same relation between radius and angle turned to find the I turn. We just use that one. But both of them will give the same answer. So 5 minutes. So first let's try to find the angle turned by motor M in 5 seconds. Okay, so again the angular speed is not a constant, so I need to get the angle turn using first principle, d omega m dt, omega m is the rate of change of angle. So d theta m, the initial angle we'll assume it to be 0, we need to find the final angle turn, equals integral omega m, which is 100 times 4 plus t dt. The time goes from 0 to 5 is equal to, that's theta m, it's 100 4t plus t square divided by 2. The limits are 5 and 0. So if you do the math on that, you get 3250 radians per second. Okay, so once we got theta m, now I'll go through the whole chain of spheres and come to the point where I can find the angle turned by E. Okay, once I can find the angle turned by E, it's just a matter of taking that, multiplying with the radius to find the height moved up. So I'm going to do it all symbolically and then do the substitution in the end. So theta m, okay, is going to be the same as theta a. Okay, you agree with me? So the angle turned by the motor m is going to be the same as the angle turned by a, because there's a shaft which connects m with a. Okay, but between a and b there's a gear, so I need to use the formula theta a Ra equals theta b Rb. So from that I can find theta b equals theta a Ra divided by Rb, which is equal to theta m Ra divided by Rb. So I sub then the value for theta as theta m. Okay, then I'm over here. I need to go from B to C. Now B and C have a shaft, right? This is a shaft. So the angle turned by B is going to be the same as the angle turned by C, because it's one shaft. So theta B or theta C is theta B, and from here, from this formula here, I can find theta C is simply theta m Ra Rb. Okay. Now if I want to go from C to D, see that between C and D there's a gear, so I need to use that formula again, theta a Ra, theta r is a constant. So theta CRC is theta d Rd. So this gives me theta d is theta C RC divided by Rd, but I know what theta C is. It's theta m times Ra divided by Rb, that's from here, times Rc divided by Rb. I think this should be wrong. This should be Rd. Okay. The final thing I need is to find theta E, but theta E and D are the same shaft, so the angle turned by both of those will be the same. I'm out of time. Give me a minute and I'll be done with this. I'm out of time. So theta E is theta D, which is equal to theta m Ra Rb. Okay, so the final step is we want to find the distance moved by the weight W, and that's simply distance moved by W is simply the radius of E times theta E. So that is theta m Re Ra divided by Rb Rc divided by Rd. Okay, so I got this from here. Theta m is known. It's 3250. I just computed it. Theta RE, RA, RB, RC, RD are all known because they're given the figure. I can plug in the values to find the distance moved is equal to, I get 2.89 meters. Okay, that's it. So I'll see you on Friday.